What is the wave equation anyway? Let's break it down. For this explanation, we'll focus on the real part of the wave equation. Although the full expression includes the complex component, the real part is commonly used because it represents the physically measurable aspects of the wave. The wave equation is a function of both space and time, where x represents the position and the t represents the time. Here the a represents the amplitude, indicating the wave's maximum value. The cosine function captures its periodic nature. Most importantly, the expression kx minus omega t is known as the phase. It determines the wave's position in its cycle and remains constant for a given point. So what does it mean when I say the phase kx minus omega t is constant? Well, the wave's phase continually cycles from 0 to 2 pi, 4 pi and so on. What we mean is that for any given point on the wave kx minus omega t stays constant. It defines fixed position on that wave, maintains the same phase over time. But what does the expression kx minus omega t equals to constant actually tell us? To truly understand what it means, we need to break down each part starting with kx. Here k is known as the wave number, or more precisely the angular spatial frequency. It tells us how much phase shift occurs per unit of distance. In other words, how many radians of phase change we get per meter. When we multiply k by a distance x, we get kx, which represents the phase shift accumulated due to the spatial displacement x. It tells us how far along the wave cycle we are at a particular point in space. Now sometimes people refer k as simply the spatial frequency, which counts how many full wave cycles fits into a unit length, like 2 cycles per meter. It tells us how tightly a wave is packed. But in our case, we are dealing with angular spatial frequency. So ultimately, the term kx captures how much the wave phase has changed just by moving through space. It accounts for the spatial contribution to overall phase of the wave. Just like the kx tells us how the phase changes with distance, omega t describes how the phase evolves over time. Here omega is called the angular frequency, sometimes referred as temporal frequency. It tells us how many radians of phase shift occur per second. That is, how quickly the wave cycles in time. When we multiply omega by a specific time t, the product omega t gives us the instantaneous phase shift at the exact moment. So in the essence, omega t captures how much phase has accumulated due to the passage of time. It is the temporal contribution to total phase of the wave, just like kx is the spatial contribution. Now, this is where it all comes together. We have seen that kx gives us the phase contribution from space, and omega t gives us the contribution from time. But what does the full expression kx minus omega t equals to constant actually tells us? Let's suppose we are tracking a specific point on the wave, say the peak of a sine wave. For a sine wave, the peak always corresponds to the phase of pi by 2 radians, so we can write kx minus omega t equals to pi by 2. Now here's the key idea. Since k and omega are fixed constants for a given wave, as time t increases, the value of omega t increases. But if the left hand side must always stay constant equal to pi by 2, then the term kx must increases as well to compensate. This means x, the position must increase. So the peak we are tracking shifts to the right over time. That shifting position is not just a mathematical artifact, it's just the motion of the wave. It shows the peak physically moving forward in space as time progresses. This is what reveals the traveling nature of the wave. The wave isn't static, it propagates through space. And this fundamental behavior is encoded directly into the structure of the wave equation. The expression kx minus omega t being constant means the points of constant space like peaks, troughs or zero crossings are in motion. In essence, this is what makes a wave a wave. Thanks for watching. I'll catch you in the next one. Until then, take care.